In this video, we're learning about decision making. Back in the 1950s, the idea of the rational planning process was developed. People were really enamored with computerization. The first mainframe computers were becoming more widely established, and the first transportation models, which we'll be talking about in an upcoming lecture, started to come about. The idea was that society can rationally decide what to do, which roads to build. We'll follow the logic of the rational planning process from the top line. We begin, get data, we define the problem, we formulate a goal, we examine, evaluate, and choose alternatives, we implement those alternatives, we evaluate the outcome, and that evaluation becomes new data for subsequent decisions. So there's a feedback loop. This is the core idea of the rational planning process, and there are details associated with it. We'll talk about those. This is a textbook version of how things should happen. This isn't an explanation of how things actually happen, except perhaps under a very bureaucratic and rational government. How do we define the problem? Well, we have objectives, we have an environment. Now this can be the physical environment, birds, trees, and things like that, but it is also the political environment, the social environment, the city, and the built environment, anything which affects the system. It says here, but are not affected by it. It might be affected by it, but that's not the critical part. Anything that affects the system is the critical part. We have resources, inputs that you can use in order to do the work. If something requires construction, then what kind of labor, materials, energy costs, and money are required to buy those things? Components, what are the elements of the system? The set of activities or tasks of the system. We have management, how are decisions made? Who is making the decisions? Who is setting the goals? Who is allocating resources? Who is controlling components? Then, how do these variables relate to each other? When we're applying this rational planning process to transportation, probably the domain in which it has been most widely thought about, we need to think about what the problem is. What are we trying to do? What are we trying to solve? Take 60 seconds, pause the video, and develop a list of transportation problems. We can list some: traffic jams, unsynchronized traffic lights, road rage, bicycle safety. There are a lot of problems. What we need to do is formulate a goal. What is the goal with respect to, say, the traffic jam at I-35W and 694? We might say increase the flow of traffic subject to safety and cost, or maximize the ratio of benefits to costs. We will talk about benefit-cost analysis in a later video. Maximizing throughput might be a good goal. We define flow in transportation as the number of vehicles per hour, the number of people per hour past a point. What if I told you that the traffic jam might be maximizing flow? You still don't like it, right? Why? Well, because you're slow. You want to maximize flow while maximizing speed. We'll get into this in the second half of the course. We call flow Q, think of it as a quantity. We call density K, think of it as concentration as spelled by a German, because that's what it comes from. As we increase, and this density is measured in, say, vehicles per kilometer, and flow is measured in vehicles per hour, the relationship between these two gives us speed. As we increase the density on the road, we're increasing the flow on the road up to a point. Slope is rise over run. Rise is flow, run is density. The slope is Q over K. What is vehicles per hour over vehicles per kilometer? Kilometers per hour, velocity. As we increase density, we're increasing flow at a fixed speed up to some point. That's the maximum flow you can get through the system. That's the capacity of the system. Ideally, you want the system to be performing at the circle. Now the system is stochastic, and this is noisier than a straight line. This is a much noisier system than you'd be used to dealing with in structural engineering or something that doesn't have people involved. But ideally, you want to be there at the circle. You want a maximized flow at a maximized speed subject to cost, safety, and so on. Your objective is to get things operating at this point. If you add cars beyond this point, you're not getting any more through the system. You're increasing the density of the system, but now the speed is lower. Speed is lower, and eventually this starts to bend downwards. Not only are you having a low speed, but you're also not getting the maximum throughput through the system at a bottleneck. If you have a series of bottlenecks, it gets a lot more complicated. We'll talk about that in a later lecture as well. Can you computationally identify all of the alternatives? There are certain kinds of alternatives that you could systematically enumerate. If your problem was, say, this is our network for the Twin Cities regions, our options are to add 0 lanes, 1 lane, or 2 lanes to every facility, we could algorithmically solve this problem. It's a very big problem to combinatorially look at every single combination of 0, 1, and 2 lanes added to every single link on the network. So mathematically, it's actually very, very hard to solve. In operations research math terms, this problem, referred to as the network design problem, is called non-polynomial complete. In principle, though, with enough computing power, one could enumerate all the solutions and solve them. That is not going to get at how you can do interesting creative designs. That kind of solution isn't going to invent a bike box at an intersection or a shared space where cars and bicycles and pedestrians are commingling within the space. If you can identify all of the alternatives, then you can optimize those alternatives given that you have a clear objective, which may be to maximize benefits, which is some function of flow and speed, subject to costs. You can solve this exactly if you have enough computer power, or maybe you can solve it heuristically if you don't have enough computer power. That really is a constraint if you're dealing with large networks. Or you can generate the alternative selectively, saying, we're going to look at these 5 things, applying engineering judgment, evaluate the alternatives, and then look for fatal flaws. For instance, you may say, bicycles in a freeway, that's unacceptable. There's a fatal flaw there because even if they mostly won't get hit, if they do get hit, they would get killed. That's really bad, so we're going to disallow bicycles on freeways. We don't want cars driving through the Mall of America. We don't allow cars on Nicollet Avenue. There are places where cars are allowed, and there are places where cars aren't allowed. We could rate the alternatives qualitatively or quantitatively. We can do what are called Delphi exercises. Delphi exercises get a bunch of experts together to look at the alternatives. They rank them, and like the oracle at Delphi, they come up with, this looks like the best, and these are the reasons why I believe this is the best. They share it with each other, and then they're allowed to look at everybody's answers and then rank them again. Often this leads to a consensus among the experts as to what the best types of alternatives are. Or we can just generate our alternatives judgmentally and then evaluate them systematically using a model. We can iterate this process. At some point we need a decision, or we need a decision that is at least as good as some threshold. We need to have some way of knowing when to stop doing analysis and actually start making a decision. Take 60 seconds, pause the video, and develop a list of constraints that keep us from achieving the goal we set out. The analyst is generally not the decision maker. The actual influence of the results of the analysis depends on the determinacy of the evaluation and the confidence of the results on the part of the decision maker and the consistency of ratings among alternatives. Evaluation is the output from a later step in systems analysis used as an input. For example, analysis leads to revisions in systems definition. Implementation experience leads to a revision of output system definition or values that underlay that definition. Is the rational planning process rational? Think about this question. What does rationality mean? Does it logically solve a problem? Yes, but there are a lot of embedded assumptions in that process that we have things like complete information, complete computing power, and that we can know what the best solution is, all of which are far from true. Not only can't we necessarily evaluate all of the possible solutions, we certainly don't have any method for generating all of the possible solutions to evaluate because those require designs. Maybe we'll have an artificial intelligence in 20 years that can do something like that. We're not there yet. We weren't there in the 1950s, and I think there are enough dimensions to design problems that we probably never will be able to systematically identify all of the possible designs for a particular solution. There's an incomplete information problem. Analysis is not free. Engineers bill by the hour, and the amount of tests that you can do are finite. Who came up with the objective? Who came up with the goals? Human beings came up with the objectives, but different human beings come up with different objectives because even if they agree that this is the cost minimizing solution or this is the flow maximizing solution, their values might be different. It might be that person A puts a higher weight on safety, B puts a higher weight on environmental impacts, or C puts a higher weight on social disruption. Those evaluation criteria are going to differ. And then, this is all driven by experts, which is great if you're a professional engineer and you're an expert, but people have different perspectives on this and they may come up with different alternatives. Are there alternative ways of making decisions? The idea of satisficing doesn't require strict rationality, and it's more like bounded rationality. We keep looking for solutions until we achieve some threshold that's good enough, satisfactory. This term, satisficing, comes from Herbert Simon, who's done a lot of work in decision theory. Incrementalism, what's the best solution for the system as a whole? It depends on what your givens are. But if we say that we want to find the best network to connect where people live, it might involve tearing out a lot of existing roads and putting in a lot of new roads. That's politically infeasible, and it's politically infeasible because people are inherently incrementalist. We're not looking for the best overall solution, we're looking for the best next step. Given where I am, and given I generally want to be over there, what's the best step that I can take now to get over there without figuring out what the entire path is and what the whole reconfiguration of the system is? How does this compare to how organizations actually function? Organizations have a set of processes and internal rules, very bureaucratic. They're bureaucratic for a reason. Bureaucracies certainly have their cost, as anyone who has dealt with the University of Minnesota paperwork understands. But these organizations have this paperwork and have this process for a reason, because without it, there would be a different set of problems. How would we ensure that you got paid if we just had to rely on people's memories? What is politics? Politics is a computational machine for evaluating different people's values and weighing those different values based on their political strength and political importance. Politicians are just calculators. They're very imperfect calculators. The values that they're using are not the values that you might have, and that is the re-election of a council member is not the value that you might hold as the most important, but that is how we've set up the political system for making political decisions that involve people with different values. There are always compromises. If one side is very strong, then usually that side might win. But in general, the only reason you might have consensus is because compromises have been made. Compromises might be within the project, or there might be side payments. I'll vote for your project if you vote for my project. Even if I don't like this project, I'll vote for it because you're doing something else for me. That's really important in politics, and that affects a lot of things in transportation, which is very annoying to people in transportation. Why does the budget for public schools have anything to do with the budget for public transportation? It does because there are people who are making trade-offs in votes in order to get things done. Then we can think about it. How do we solve this problem? We don't have to solve everything simultaneously. We can decompose the problem into strategic problems versus tactical problems versus operational problems. We're not worried about operational problems when we're making strategic decisions. We assume that someone will handle that. We have to understand how the operations work in order to be able to do that, and there are different ways of making decisions.